Okay, so you've written down whether or not you think it's better to go first or second, or whether it doesn't matter at all. So what we're going to do is we're going to apply statistics to this. We're going to look at data. The first data we've got here for us to look at is actually what happened in all of the Jimmy Fallon games that happened on his show. Now, previously, we just looked at what happened with the first egg in each game. But what I did was I went back and watched all the games through to the end. And as it turns out, the minimum number of eggs it takes until a winner is crowned is 3. Tom Cruise was one of these games, happened with 3 eggs. Because if the first person gets a raw egg on the first draw and then gets a raw egg on the third draw, then the game's over. It doesn't matter what happens with the second person. So the minimum number of eggs is 3. The maximum number of eggs is 11. This one's a little bit trickier to think about, but it's possible, and it happened. I think this may have been Bradley Cooper. I can't remember exactly. But if the first 8 eggs that come out of the carton are all hard-boiled, that means the game effectively is over. That means the 9th egg will be raw, the 10th egg will be raw, and the 11th egg will be raw, and then whoever drew that 11th egg loses. So the maximum number is 11 eggs, the minimum number is 3, and there's any possibility in between. The one we saw was Peyton and Magic. It's right here. That took 5 eggs. Peyton got raw, Magic got raw, Peyton got hard-boiled, Magic got hard-boiled, and then Peyton got raw. And then Anna Kendrick and David Beckham and whoever, Doogie Howser, they all are one of these data points up here. So 2 games lasted 3 eggs. 1 game lasted 4, 1 game lasted 5, 7 games lasted 8, 1 game lasted 9. Now I want you to take a look at this graph and see if you can figure out, was it better to go first or second? Okay, well, this might be an easier way to think about it. These numbers down here, 3, 4, 5, 6, they do tell you something. For example, in these games here, these 2 games that lasted 3 eggs, the first person must have lost. Because the only way for the game to be over with 3 eggs is if the 3rd egg was raw. And if that ended the game, that means the first egg was also raw. Hopefully that makes sense. You know, with Peyton and Magic, Peyton went, this is just Peyton now, Peyton went raw, hard-boiled, raw. But it ended at the 5th egg. 7, if it took 7 eggs to go, that means the first person definitely got a raw egg on the 7th egg, but they also got a raw egg either on the 1st, the 3rd, or the 5th. So any game that took an odd number of eggs was lost by the first person. Conversely, any game that took an even number of eggs was lost by the second person. So another way of looking at this data is actually right here. This is what happened with Jimmy Fallon's games. 33% of the time, the person going first loses, and 67% of the time, the person going second loses. Said a different way, 33%, or roughly 1/3 of the time, the second person won, and 2/3 of the time, the first person won. Now, what's so funny about this is, Jimmy often plays the game. You may remember this from the videos we watched before. Peyton and Magic actually is the only game Jimmy himself didn't play. He often plays, and he always has his guest go first. And what's hilarious is the number of times Jimmy looked upset because sitting second, he was often losing. He wasn't winning very often, 1 in 3 games roughly. So that made me want to kind of question this data. What would happen if we played more and more games? So I decided to build a Russian egg roulette simulator. Let's take a look at that now. So what you're going to see here is a similar simulator to what we saw back in the last series of videos when I was just worrying about smashing the first egg. But now I've taken it further than that, and now we're smashing all the eggs and keeping track of how many it takes until one of the guys loses. So that's what we're going to be graphing here in this bar graph, is what percent of the time the first guy loses, which is Peyton, and what percent of the time the second guy loses, which is Magic. And of course, this extends beyond Peyton and Magic to anybody playing. So what percent of the time the first person will lose, and what percent of the time the second person will lose. So just like we did before, I'm going to let Excel kind of take it away and let the results kind of speak for themselves. So let's hold down the F9 button and let it go to work, and we'll collect the data in a little bit. Okay, my friends, so what you're seeing is, I think it's fairly stable at this point, at 56% to 44%. So after, I mean, I don't know how many trials we've run on this thing. I'm going to guess probably, yep, about 6,000 trials. 6,000 trials, and 56% of the time, the person going first loses. And this is very telling, I think. I think this is very telling. Jimmy always goes second when he plays. And he says, as the guest of the show, you get to choose first. He's actually putting his guests at a mathematical disadvantage. But what I find amazing is, it's backfired on him. So you might remember this graph being what happened over Jimmy's 18. Okay, and this is what Jimmy saw. And we also saw he ended up losing 2/3 of the time. But what was actually supposed to happen was more like this. This is actually the cumulative results of all of the games that we saw over here. The 56% of the first person losing, that's these 2% plus this 8% plus this 15 plus that 17 plus that 9. If you add all those up, that's where you get your 56%. And if you add up this 5, that 12, that 17, and that 15, that's where you get the second person's 44. So poor Jimmy, his results didn't look enough like this. He had the spike at 8, but he hadn't played enough games to actually see the actual shape of this distribution, which is, again, one of the warnings of having too small a sample. You end up with situations like this. That is just one of many applications of what I think of as dependent probability. Depending on what egg comes out in the first round, colors entirely what's going to happen in the second round and beyond. And in the last video here, we'll look at the differences between independent and dependent probability. They exist both in Vegas, in casino games and things like that. More so than just Vegas, they also exist outside of casinos when we apply probabilities to life. Let's take a look at those next.